On a starry night, an aura of mystery filled the streets of the city. The Royal Museum, known for its splendid artifacts from bygone eras, kept a treasure hidden in the dark. But on that fateful evening, everything was about to change. An international gang of art thieves, notorious for their skillful heists, had zeroed in on the museum. They planned the perfect burglary to steal an artifact of incredible value, the legendary diamond of the pharaoh's crown. For our game, we used the following art gallery problem as a foundation. The art gallery problem, also known as the museum's problem, stands as a prominent and extensively examined visibility issue within the domain of computational geometry. The practical inspiration behind this problem lies in the realm of security and surveillance. This problem also formed the foundation and inspiration of our board game. But first, let's explain what the mathematical offers in terms of theorems and solution approaches are.
The main question is, given an art gallery, what is the smallest quantity of stationary guards required to ensure the room's protection? It's very easy to notice that a room in an art gallery, or rather the walkable playing field of our board game, is an orthogonal planar polygon with some holes in it. For any polygon with these features exists an upper bound for the amount of guards necessary to cover the whole area. This was shown by Hoffman in 1990. N divided by 4 and rounded down, guards are sufficient to cover an orthogonal polygon of n vertices with h holes. We will provide a swift visual representation of the approach for an orthogonal polygon without holes. First, we count down the amount of vertices, which in this case would be 12. Then we'll do a convex quadrilateralization to divide the polygon into multiple smaller units, each containing 4 vertices. Following that, diagonals are introduced, interconnecting the vertices of these miniature polygons. That results in a graph that can always be 4-colored, which is therefore the next thing we do. Last of all, we choose the color with the smallest amount of vertices and get our desired upper bound. Hoffman's theorem can also be applied to our playing field, but covering the entire area would not be very fun, so the number of guards is actually being reduced to an enjoyable number.
The main objective of our game is finding treasures and achieving to bring them back to safety to score points. But the biggest treasure of all, the diamond of the pharaoh's crown, waits at the end of the game, leading to the greatest hunt of all. The game consists of a modular field with one inner ring and one modular ring on the outside, made of 8 modules. With that, we have our planar orthogonal polygon with holes. There are 3 pawns per person with individual dice per pawn. They need to collect treasures, which are situated on the outer ring, on the yellow fields. With these pawns, you can also collect action cards on the purple fields. For example, there are handcuff cards, which permit a player to knock out an opponent, and if he or she is in possession of a treasure, to steal a treasure from him or her.
Besides, there are 2 guards walking on a predetermined path. After every player has made their move, it's the guard's turn. To determine whether the guards look around for players, a guard dice is thrown. To increase the danger level when the guards are not activated in a round, the probability for an activation increases with every round. To achieve this effect, the guard starts with a 6-sided dice. If no 1 is rolled, a dice with fewer sides is used in the next round, and so on, until a 1 is thrown and the dice gets reset to a 6-sided one. On activation, the guards throw every player in their side back to its starting field. To better see if the guards detect the pawns, we included a laser block. Because of our 3-dimensional wooden cubes, which are the walls, you can exactly see if the laser hits you.
Once one player has collected 3 artifacts, the inner ring is now free to be explored. The game ends once one of the players collects the main treasure. This is our last version of our game. We tested many versions of it, and with this version we tried to solve all the problems we had in the earlier versions. We enjoyed playing our game because it was fun to be on a hunt after the treasures and to avoid the guards and look for the best strategy to win the game. Our game Museum Heist, along with other games with a mathematical background like Set or Dobble, show that math doesn't always have to be obvious to the player, but still plays an important part behind the curtains.